So, Jeff, you used to work on exploding stars. And one thing I've always wondered is a lot of exploding stars happen because there are two stars close to each other, right? And one star is grabbing material off the other one, and it gets to a certain mass where it can't sustain itself and it explodes. So, in that situation, what happens to the other star?
Well, it doesn't have a great day, but it's actually mostly okay. I've done a couple of projects where we looked for stars that had weird elements on their surface you wouldn't expect that maybe came from the explosion. But a really cool effect is when you have these two stars in orbit around each other, one explodes, the other one can go flying off into space. And so we've got an expert on that topic with us today, Dr. J.J. Hermes, who is a postdoc at UNC Chapel Hill, a friend of ours back when all three of us were at UT Austin. And he's done some recent work on these exploding stars and flinging one off into space. So welcome, JJ.
Thanks.
So start us off here. We have these two stars. They're orbiting around each other. They've got gravity pulling on each other. One explodes. One goes flying off into space. So first off, why does that happen? What's the basics of the physics there?
It's a slingshot, basically. So imagine if you had two stars that both have mass. They're both going around each other very quickly. And then another star loses all, if not most, of its mass. Then those two stars are no longer gravitationally bound and they get slingshot. So I think it's really important that the two stars need to be really close together for this to be a very impactful event and for the stars to actually get slingshot to really high velocities.
So, how fast are we talking, these stars that are being flung away?
Fast enough to be ejected from our galaxy. So our galaxy has a lot of gravitational potential. And we think if a star goes above several hundred kilometers a second, more than 1,000 kilometers a second in some of these cases, that they're no longer bound to our galaxy and they get flung off into intergalactic space, which is a very cold and desolate place. I mean, if interstellar space is cold and desolate, intergalactic space must be even worse. I don't like thinking about it.
All right, so these stars are moving really fast enough to escape the galaxy's gravitational pull, but they're still not moving so fast like shooting star you would see it with the human eye, right? Like not quite that fast. But how do we detect, these fast-moving stars faster than, your typical star?
Recently, a lot of people have been using what's called Gaia. There's a European space mission that's been had a recent data release in April, and so people have been mining that data set. It's more than 1.5 billion stars. So not only do you get the position of the star, but you get a good estimate of how far away the star is from us and how fast that star is moving, sort of in 2 dimensions on the sky. So it's proper motion. And so basically the simplest way to shortcut to find these stars is to look for stars that are just moving across the sky much more rapidly than you'd expect just a normal star to be moving.
So, for comparison, our own sun is moving around the galaxy at, say, 200 kilometers a second, right? Is there any other reason that other stars might be going at, say, 1,000? Anything other than being flung away from an explosion?
Yeah, so the fastest stars we used to know about in our galaxy were very likely ejected from the center of our galaxy. There's a supermassive black hole there, something like 1 million times the mass of the sun or more. And if a star gets too close to that black hole, just like in our own solar system when we try to send spacecraft to Jupiter or to Pluto even, we use gravitational assists from planets in our solar system. And so if a star gets too close to the black hole in the center of our galaxy, it can get a really massive boost. And sometimes it can get ejected from our galaxy that way. And so in the past, that's been one of the best ways that we've hypothesized that these stars can get such high velocities. But it's really fun to think about stars that were in very close binaries before one of them blew up to give that other star a really high velocity.
So people have been looking for these kinds of stars, it's been theorized this is what happens to the partner star when one explodes. And then Gaia had this big data dump a few months back. And then you and some collaborators jumped on this, and a few other teams jumped on this as well. So tell us a bit about that story and how that all came out.
Yeah, so recently it's really been groups led by Ken Shen at Berkeley, and then Roberto Ratti was an old office mate of mine at the University of Warwick in central England. And so he's also been trying to find some of these systems in Gaia. And I have to say, it's actually been so far, it's been a very productive collaboration between Ken and Roberto. We've shared targets that we've started looking at together. And so, so far it's been one of the nicer experiences when groups try to work together.
You sound surprised by, people getting along with each other, and that is not the norm, I think many of us have found.
Certainly not been my experience.
I feel as though I'm lucky to work in the field of researchers who work on just stars. They don't work on stars that do anything super explosive, and so I feel like our pace and relaxation scale seems a little bit more mellow than some of the other subfields of astronomy. And so when I get to work with people in the transient community or one of these communities, people trying to follow up kilonova or one of these things, right, where every second counts. It's a bit it's fun, but it's also a bit stressful, and so my hair grays faster when I work with those folks. But it's a lot of fun because it is sort of at the frontier of what we know about these really, really energetic explosions in our galaxy and across the universe.
So that sounds like a nice, fun, relaxed area of astronomy. How did you get into that field?
So like I say, I shared an office with the guy Roberto Ratti at the University of Warwick, and there was this old catalog of candidate white dwarfs called the GD sample, not the GD that everybody uses when they stub their toe. This was the guy Henry Gickless. He was just monitoring a bunch of stellar proper motions from Lowell Observatory. And he put together about 1,700 candidate white dwarfs back in the 50s, 60s, and 70s. And so this candidate list has existed for a really long time. But a few years ago, we realized that a lot of these stars don't have spectroscopic follow-up. And so Roberto was at a 1-meter telescope in Italy, and this was one of his candidate white dwarfs. And it turned out to be one of these really fast-moving white dwarfs. It had a radial velocity, that is the velocity coming towards us or going away from us, of 500 kilometers a second, which is really, really fast. And so when you factor in how fast it's moving in 2 dimensions, it's something like 850 kilometers a second. So it's certainly leaving the galaxy. And we don't know if it was actually the star that blew itself up or the companion to the star that blew itself up, but it's got a very weird abundance pattern. It doesn't have any hydrogen or helium, which is basically the sun is more than 99% hydrogen and helium. So this thing had really, really energetic nuclear processing, which happens at the end stages of stars before they blow up. It's mostly neon by mass, which is weird. It's this lit up sign in the galaxy that's moving super fast. It crossed the plane of our galaxy less than 10 million years ago. And in another 5 or 10 million years, we're going to lose sight of it. So we're really lucky to have caught it. Another group caught it before we did and published it in Science before we could. So we were on the losing end of that fast-paced part of this field, but we keep trying to find more of these with Gaia. So this is far afield from what I usually work on, but it seems like a really fun diversion. And this is sort of what we do as astronomers, is just keep looking for new weird things. And certainly stars that are leaving our galaxy are really weird.
So obviously Gaia is still up there taking a lot more data. So we're expecting to see a lot more of this over the coming years. So good luck and thanks for joining us. Cheers.
Yeah, thanks so much. This has been fun.